A factory that burns off polluted air can waste most of its fuel heating exhaust that vanishes up the stack, unless something catches that heat on the way out and hands it back to the next breath of gas coming in. A honeycomb ceramic is that heat bank, a solid grid of thousands of tiny channels that soaks up heat from outgoing gas and releases it to incoming gas, turning waste heat back into the process. The whole value of the structure is surface. By dividing a solid block into thousands of thin-walled channels, the honeycomb packs an enormous internal surface into a small volume, and it is across that surface that heat passes between the ceramic and the gas flowing through it. In service, the block is heated and cooled every few seconds as the gas flow reverses, so it has to take constant thermal shock without cracking. A low coefficient of thermal expansion lets the thin walls swing through hundreds of degrees again and again while holding their shape, the property that decides how long the block lasts. The straight, parallel channels also let gas pass with little resistance, so the fan pushing air through the block spends little energy fighting it. High surface area, low flow resistance, and stability under thermal shock are the qualities that make the structure work. The fineness of a honeycomb is measured in cells per square inch. Packing more cells into the same face raises the surface area the gas can exchange heat across, but it also narrows each channel, which raises the resistance to flow. Choosing the cell density is a balance between how much heat the block should recover and how hard the fan must push. More surface, or less pressure drop. The way the heat is recovered is a cycle. Hot, clean gas leaving the burner pours through one honeycomb bed and gives up its heat to the ceramic. Then a valve reverses the flow, and cold, dirty gas coming in picks that stored heat back up before it reaches the flame. With beds alternating like this, a regenerative thermal oxidizer built on honeycomb ceramic recovers roughly 95 to 97% of the heat, so the burner adds only the little that is left. That recovered fraction is the whole point. Because the honeycomb hands almost all the heat back, the flame needs only a small amount of fuel to keep destroying the pollutants in the gas. The structure turns a heat-hungry process into an efficient one. Honeycomb comes in modular blocks that stack to fill a bed. Square blocks around 100 or 150 millimeters across and up to a few hundred long are common, cylinders where the housing is round, and the wall thickness and cell count are set to the cell density the process needs. Anywhere from a coarse 10 up to a fine 600 cells per inch. Building a bed is a matter of stacking those modules to the volume the gas flow calls for. Block size, channel shape, cell density, and wall thickness are each chosen for the flow rate and the temperature, and the number of blocks sets the bed height. Taller beds recover more heat, so the stack is sized to the efficiency the process is designed around. In a regenerative thermal oxidizer cleaning solvent fumes from a coating or chemical line, honeycomb beds sit under the burner and do the heat work. Dirty, fog-laden air is drawn through a hot bed that preheats it almost to ignition. The burner finishes the job and destroys the organic compounds. And the cleaned, still hot gas passes out through a second bed, loading it with heat for the next reversal. Because the beds return almost all of that heat, the flame burns only a trickle of fuel to hold temperature. And the low flow resistance of the straight channels keeps the fan power low as well. Season after season, the beds ride the same swing, heated and cooled thousands of times as the valves reverse, and the low expansion ceramic comes through it without cracking. Pulled for inspection, the channels are still open and square where thermal fatigue would have crazed a lesser material. Efficiently, a grid of ceramic channels turns a fuel-hungry cleanup into one that mostly runs on its own recovered heat, the quiet core of a clean stack.